With that, I'm going to introduce our speaker here, Zach Easton from Virginia Tech, who will be making a presentation on soil hydrology. And please give him your attention, and we welcome you to crop school.
Thank you. Thanks. So, handed out some fact sheet. We ran out. I don't know if we can get more made. We probably need 30 more. So maybe afterwards we'll see about getting more of those made. I'm not sure if we'll do that or not. It just provides more detail of what I'm going to present today. So it might be a good resource. You might be able to use it to start a fire. So I see this class is a little bit more proactive than last one. We didn't have anyone in front of that column in the last class, so this is good. Just like class, it doesn't matter if you're 15 or 50, you want to sit in the back. So I'm Zach Easton from Virginia Tech Biological Systems Engineering. And I'm going to talk today briefly about soil hydrology, the basics of soil hydrology. So just some goals for what I'm going to discuss today. So the first is I'm going to introduce the concepts and the components of the hydrologic cycle. We're going to talk mainly about the soil hydrologic cycle. You could look at it at a watershed scale, but we'll sort of distill it down to a soil level. So we'll highlight some of the hydrologic concepts and applications important in agroecosystems in the Mid-Atlantic. We'll discuss how knowledge of the hydrologic cycle can improve things like crop production, environmental quality, etc. So here's an overview of the landscape or watershed scale hydrologic cycle. Now I said we're not going to discuss all of the components. We'll focus on the soil system. So we'll look at evapotranspiration, precipitation, runoff, overland flow, infiltration, and percolation interflow. We're really going to ignore groundwater, base flow, and stream flow, but just recognize that there are other components that we're not going to discuss. And if you can't hear me, speak up and I'll try and speak louder. So first, precipitation. I think everyone knows what precipitation is, but just so we're on the same page, I'm going to define it how I define it. So precipitation is the condensation of atmospheric water vapor that falls under gravity, and the amounts and types of which affect things like soil development, vegetation growth, and then transports of soil nutrients off of our fields. So important factors are the annual amount and phase, so how much falls over the course of a year and what phase. Is it rainfall or is it snowfall, hail, things like that. The intensity and raindrop size, so do you get 3 inches falling in an hour or does 3 inches fall in a month? That's important in our systems as well. The duration and frequency, again, this relates to number 2. But are we getting high intensity rainfall events occurring at an infrequent time scale? So we get 10 inches of rain falling in one event, and then we don't get rain for the next 6 months. And then the seasonal distribution. Are we getting adequate rainfall during the growing season? Are we getting adequate rainfall during the non-growing season to recharge aquifers and soil storage? So this is just a screenshot from the National Atmospheric Deposition Program of 2013 precipitation in the Mid-Atlantic. Well, the whole U.S., but I'm highlighting the Mid-Atlantic. And this is a pretty typical year in terms of the total annual precipitation that we tend to see across the Mid-Atlantic. We get anywhere from about 40 inches to about 55 inches across much of the Mid-Atlantic. We tend to get a little bit more along the spine of the Appalachians due to that orographic effect, a little bit less as we move into Pennsylvania and things like that. But this is pretty typical. And just remember this, because when we talk about evapotranspiration, I'm going to come back to this figure briefly. So when we think about rainfall, particularly from an engineering standpoint, we like to think about it in terms of rainfall return variance and probabilities. So anyone who does any engineering here will be familiar with what these are. But basically, a rainfall return period is something like a 2-year rainfall, right? So a 2-year rainfall would be a rainfall that would be expected to occur once every 2 years. The probability of occurrence is once every 2 years. And then this is the duration of that rainfall. So a 1-hour rainfall that occurs once every 2 years. And what this isotherm map shows is what those rainfall amounts are depending on where you rest. So if we look at the Mid-Atlantic, I'm sorry this is a little grainy. For instance, let's look at this 1.4. This is 1.4 inches of rainfall occurring in 1 hour, and the probability is 2 years. So we can look at where that isotherm crosses our region. So it goes from West Virginia through Virginia, Pennsylvania, into New Jersey. What that says is that we have a once in 2 year probability of having a 1.4 inch rainfall occurring in 1 hour. If we look at the 24-hour 2-year probability, we see that it's a much larger volume. So if we look at that sort of similar isotherm, it's about 3.5 inches expected in a 24-hour rainfall occurring once every 2 years. Finally, this is sort of the mother of all rainstorms. This is a 24-hour, 100-year probability rainstorm. And so we actually had a 24-hour, 100-year rainstorm in Southwest Virginia this year, about 2 months ago. You can see that most of the region falls somewhere between 10 inches all the way up to about 5 inches in central New York, Pennsylvania. So that means that the probability of, say, an 8-inch rainfall occurring in this area in 24 hours is once every 100 years. And I think when we all think back to the past few years of rainfall events, we've seen lots of events that might fall in this, but certainly that fall in that 2-year, 24-hour period. 4 to 5 inch rainfall events over the course of the day are not that uncommon. So it's not really, you're not saying these events don't occur, it's just that the probability of them occurring in any given year is once. So rainstorms of high intensity and for long durations, like this, are the ones that are most likely to cause our water quality and erosion problems across these watersheds, across our watersheds. So what are some examples of storm intensity and raindrop size and duration frequency? So I'm sure some people have used the Russell model, the revised universal soil loss equation. And so in this model, there's a factor that's called R, which is the rainfall and runoff erosivity factor. And this determines the kinetic energy produced by a given storm. And so it's determined for all storms throughout a year from different geographic regions to calculate that R value. A second example would be for the design of water management control structures. So stormwater control structures are sized based on a probability analysis of the recurrence of a storm of a different duration intensity. So a 100-year storm return period implies infrequent but very large hydrologic events, whereas a 1-year storm return period would be relatively frequent and smaller events. So if you want to design for a large return period storm, you'll have a much greater level of protection or reduction in risk that a structure might fail. For instance, a constructed wetland, if you design it for a 100-year storm, it's going to be a massive constructed wetland. It's also going to be very expensive to build. Well, those are some considerations of how return periods can be used in design of different practices. So, evaporation. So I wanted you remember. I told you to remember that map of the U.S. in terms of precipitation. Well, this is the similar map for evapotranspiration across the United States. And if we look in the Mid-Atlantic region, you probably can't see this legend. So dark blue is 10 to 20 inches of evapotranspiration a year, and then all the way up to 40 to 50 inches of evapotranspiration per year in southeast Virginia. And so what you can see here is that we get 40 to 55 inches of precipitation a year, and in some areas of our region, almost all of it is potentially removed by evapotranspiration. Whereas in these northern Pennsylvania, New York, down into West Virginia, maybe only a third to a half of it is potentially removed by evapotranspiration here. And we'll come back to this when we look at calculating a water budget for a field. How much water is removed by evapotranspiration versus how much falls. So what is evapotranspiration? Evapotranspiration really has two components. And the first component is evaporation. And evaporation is the process by which water vapor, which liquid water or solid water, snow, is removed from the soil or surface and enters the atmosphere, or the gas phase. Generally, we're not too concerned about sublimation in terms of agroecosystem productivity, but we're concerned about liquid water movement in the gas phase. And so evaporation is measured a couple different ways. One of the most common is via pan evaporation. And that's the water loss per unit time to the atmosphere from the water surface. And it's measured using one of these standard, this is a class A pan right here. So what you do is you fill this with water, and every day you go out and measure how much water is removed, converted to gas, and removed to the atmosphere, and you refill it to a certain level. And that approximates your evaporation level. And then you can apply sort of crop factors to convert it to crop-specific numbers. So corn might have a pan factor of 0.8, soy might have a pan factor of 0.7, etc. So the evaporation rate from a wet soil is very similar to a pan. So you can imagine a wet soil as just a saturated soil, dump soil and this is saturated. You're going to evaporate it almost the same rate you do as a standard pan. Where it gets interesting is that as the soil dries out, the evaporation rate from the soil decreases relative to the pan evaporation because the soil surface cannot readily conduct this water. So water is held more and more tightly in that soil matrix as it dries down and it can't be removed by evaporation. This is just a figure showing how that might work out. So we have soil moisture on the x-axis, saturated soil here, and then soil drying here. And at soil saturation, your evaporation is as high as it's going to get. So you can't remove more moisture than from a saturated soil. As the soil dries down, your evaporation rate falls until you reach what's called the wilting point down here. And you'll have a much lower, the atmosphere cannot remove more soil moisture once you reach that point. It's held too tightly in that soil profile. So the other component of evapotranspiration is what's called transpiration. And this is really the important one in terms of crop systems. So transpiration is the process by which water moves through the plant tissue and evaporates from the leaf surface. And if you see my third grade drawing down here, it just shows how this might happen. So water is absorbed by the roots from the soil system, and it travels through the plants where it's evaporated from that leaf surface. And so there are two important hydrologic components of transpiration in the system. So the first is that large evaporative surfaces provided by that plant canopy, the leaves, allows for higher evaporative losses from the system and greater plant cooling. So that's why plants don't die necessarily when it's 95 degrees out. As long as there's soil moisture, they're able to cool themselves with this process. The second is perhaps a little bit more interesting. So water that's stored in that soil can then be utilized as sort of a buffer between rainfall events. So you get a rainfall event, it infiltrates the soil. The plants can access that soil moisture for a period of time to provide this plant cooling. Whereas if the soil was dry and they can't provide that plant cooling, and they would tend to die. So the combined effect is called evapotranspiration, and it's the combined effect of evaporation and transpiration of water. And there are two ways to think about evapotranspiration. The first is called potential evapotranspiration, or PET, and this is really a constant. This doesn't change if you have the same solar radiation, temperature, humidity, and wind speed. It's not going to change if those conditions are constant. The second is called actual evapotranspiration, and this really depends on the time of the year, the stage of plant growth, and the available soil moisture. So the actual evapotranspiration changes over time. It'll change every day. It'll change over the course of the day based on these factors: time of year, stage of plant growth, and soil moisture. So again, we saw that in that other figure, but as the soil dries out, AET, actual evapotranspiration, will decrease because the matrix potential of that soil increases. So the soil is holding that water more tightly. You're going to have lower actual evapotranspiration rates. This is just a figure showing what that might look like for a soil profile. This is, let's say, millimeters of water divided by 25.4, and you get inches of water. And this is days from the beginning of the growing season. So say in April, you have a relatively high soil moisture, the soil is saturated, and we just met with snow, you got some spring rains. And you can have relatively high actual evapotranspiration rates because the soil is not holding that water very tightly. There's excess moisture. As we proceed through the growing season, plants are removing soil moisture, soil water, so that's falling. The soil moisture level falls. You get a concurrent fall in that actual evapotranspiration. There's less moisture to remove. Hence, plants remove less of the moisture. End of the growing season, maybe you get some big rainfall event, soil moisture goes back up, but now the plants have senesced, so you have much lower soil moisture continuing the rest of that season. And this is my 10th grade image of evapotranspiration, so transpiration plus evaporation. So runoff and infiltration. Now I considered splitting these up into two different subheadings, but they're really tightly coupled. So I'm going to discuss runoff and infiltration together. And it was sort of up in the air as whether I should prevent infiltration first or runoff first. But again, I decided to go with runoff first. So what is runoff? I think everyone can visualize what runoff is. It's water moving across the soil surface. And it's actually a little bit more complex than that. We'll get into this in a minute. But runoff, technically, I define as the portion of precipitation over an area that's discharged from that area through stream channels. That doesn't really mean a whole lot, but maybe in a few minutes it'll make more sense. So we can define runoff sort of in two different ways, and it really depends on your field. So the water that is lost directly from the soil surface is called surface runoff. And in these images, you can see this water right here. That would be surface runoff. Now, in soil science and agronomy, runoff is usually referred to as the water lost by that overland flow, so direct surface runoff. So in the hydrologic sciences, runoff would include both that surface flow and shallow subsurface flow, what we call interflow components. So you can imagine across this hill slope, let's say right here, water that's infiltrated up at the top of this hill slope is flowing down this slope through the shallow soil profile. And once it hits these saturated areas, it exfiltrates, it expresses itself on the soil surface and creates more runoff. So this image is one that would include both that overland flow and the interflow component. And this one is really just overland flow being generated here. It's probably a little hard to see. We can come up if you want. And so, again, these are two different processes that are generating runoff. Really, there's infiltration excess runoff and there's saturation excess runoff. So runoff that is generated by infiltration excess processes is really surface water that has not infiltrated the soil profile, as the name implies, infiltration excess. So it occurs when the rainfall rate, so the rate at which rainfall is falling, is greater than the soil infiltration. So you get 2 inch per hour rainstorm, the soil can only infiltrate 1 inch per hour, you're getting 1 inch per hour of runoff. So runoff generated by saturation excess processes is surface runoff that may or may not have infiltrated that soil profile. And so, well, I'll show an illustration of this in a minute, but rain falling on a saturated area might not ever infiltrate the soil, but it does generate runoff. The other two processes would be interflow and percolation. Really, they're water components that have infiltrated the soil, but because of different subsurface soil features or scale effects, it does not remain in that soil storage. So maybe there's some sort of a shallow restricting layer, plow pan, shallow bedrock that prevents percolation of that water deeper in the soil profile. And so at some point the landscape is going to exit that soil profile and generate runoff. So water that infiltrates but does not stay in that storage and eventually becomes runoff to streams, there's many different terms to describe them. I've listed a few here. So interflow, through flow, return flow, base flow. And the exact terms really depend on how that water is moved through the landscape. And I'll show an example in a minute again. So saturation excess runoff occurs when the soil profile becomes saturated and cannot infiltrate more rainfall. The specific flow path that the runoff takes has implications for water quality at the landscape and watershed scale. So infiltration excess runoff tends to create more erosion. You get a lot of sheet and rill erosion occurring on fields from infiltration excess runoff. Whereas saturation excess runoff, you tend to get more things like stream bank failures, near stream erosion, things like that, where you've got high moisture content in the soil that loses its cohesivity, and you can get that type of failures. So, in short, surface runoff equals precipitation minus infiltration minus surface storage. And I wanted to bring up surface storage because in a lot of the agroecosystems, this is an important component of surface runoff generation. So if all the precipitation infiltrates the soil, that is the rainfall intensity and amount is less than the infiltration rate and capacity, then we don't get runoff occurring, right? However, if the rain intensity or amount is greater than the infiltration rate or capacity, water can accumulate on the soil surface. And so if the surface is smooth, and the infiltration excess quickly results in overland flow, which can lead to sheet and rill erosion on those low cover soils I just mentioned previously. So if you have a soil, let's say a tilled soil, where you get significant furrows occurring across that landscape, you can get what's called surface storage or depressional storage. And so that refers to the amount of water that can be held on the soil surface before overland flow occurs. So these small depressions on roughly tilled fields can actually hold considerable amounts of runoff, delaying the onset of off-site movement. And this is just a picture of what that might look like. So these areas obviously are holding water. There's no runoff leaving this field, but if we get additional precipitation on that field, we might finally fill these surface depressions and then create runoff. So what's the effect of the rainfall intensity? So again, we're thinking about the infiltration excess runoff processes. So in this system, surface runoff occurs, again, when rainfall intensity is greater than net soil infiltration. So the type of runoff depends on the infiltration capacity of the soil and may occur anywhere in the landscape where soils with low infiltrability occur. And so this is just an example of two different rainfall rates. 3/4 of an inch an hour falling on the same soil, right? So this soil has an infiltration capacity of 1 inch per hour. If you get a 1.5 inch rainfall event falling per hour event falling in this soil, 1 inch per hour will infiltrate, and 1/2 inch, the remainder, will run off. Now, if you get a rainfall rate of only 3/4 of an inch an hour falling on this soil, all of it will infiltrate because it has a higher infiltration capacity than the rainfall rate. So that's an example of how infiltration excess runoff would be calculated in this example. So what about the other type of runoff, so saturation? So I'll give an example of both with this sort of hill slope. So I've exaggerated what a hill slope might look like. So on this hill slope, again, we're putting in some sort of a plow pan or some sort of restrictive layer that impedes the vertical movement of water through that soil profile. So it tends to give you hillside drainage. You get water flowing along that restricting layer across that hill slope, creates stream flow in this case. So when we think about this in terms of the infiltration excess runoff processes, let's think about it. We get a constant rainfall falling across this hill slope, let's say 1.5 inches per hour. You get 1 inch per hour of infiltration, and the remainder, 1/2 inch per hour, is surface runoff that leaves this hill slope and generates stream flow at the bottom of the hill slope. And so anyone who does engineering would know what the curve number is. The curve number method to calculate runoff is based on this infiltration excess runoff method to determine runoff across a field. And this is an image. This is a new pad getting ready to be used here. The runoff rate is relatively constant across this entire pad. It's compacted so you don't get much infiltration. You get the surface runoff leaving this area. So we asked the question, how common is infiltration excess runoff across areas in the Mid-Atlantic? So we did a generalized analysis of the probability of an area generating surface runoff for different return periods. Now we discussed briefly what return periods mean in terms of storms. So a 1-year return period, relatively frequent, lower intensity, lower volume of rainfall. 100-year storm, very infrequent, very high intensity, very high volume of runoff per month, this by month. So on the y-axis, it's showing the percent of the area, whether it's a field or a watershed, whatever unit you want to use, that generates that infiltration excess runoff. So from 0, no infiltration excess runoff, all the way up to 100% of the area generating infiltration excess runoff. And what you see here is that during the time of the year when we get most of our precipitation, 78% of it falls from March through September, it's very rare to see any infiltration excess runoff being generated. You need to be above a 10-year return period storm before you start seeing really any area with watershed generating infiltration excess runoff during this time of year. However, during the bulk of the growing season, we tend to get these much more intense convective type thunderstorms, and we do see 3, 4, 5 inches per hour potentially being generated, rainfall being generated under those storms. And in those cases, we do start to see some of that infiltration excess runoff being generated, particularly for storms less than a 2 or 3 year return period duration. So not only does it depend on the soil properties and things like that, it also depends on your rainfall and the time of the year as well, depending on which type of runoff is being generated. So if the bulk of it really isn't infiltration excess runoff, what's the other process? And that again is saturation excess runoff. And so here, topography and soil depth really govern where runoff is generated. We have this same hill slope, right? We get rainfall on that hill slope. Let's say this is an inch per hour rainfall. It's less than the soil infiltration capacity. The rainfall will infiltrate that soil profile until some areas saturate. So once some areas of this landscape saturate, rain falling on those areas becomes that saturated overland flow. Now you also get, interflow. When we talk about interflow, so rain that's infiltrated the soil up here flows down this hill slope, and once it hits that sort of saturated area or saturated edge, can exfiltrate the soil profile. So you have infiltrate, which is movement into the soil profile. Exfiltrate is movement out of the soil profile. So we can get exfiltration of that water in these saturated areas of the landscape. So it's a little bit more complex of a process, a little bit more of a challenge to try to figure out where it's occurring in the landscape. And so this type of runoff really is not sensitive to rainfall intensity or to soil type, aka the infiltration rate, but depends on where these saturated areas of the landscape occur. We tend to see them occurring in a lot of cases at the bottoms of these long slopes where you get a slope change or where you have a shallow soil layer somewhere in that soil profile. So now we talked about runoff. Let's talk about sort of the analogous component, infiltration. And so infiltration is the downward entry of water through the soil surface into the soil, and it's a result of gravity and the soil, basically soil suction. The soil can suck water down into the soil profile. So the infiltration rate refers to the quantity or volume, the amount of water per unit area, per unit time that enters the soil. And you can measure the infiltration rate. This is with a ring infiltrometer, and here we're doing a dye test, trying to figure out the flow paths that water takes once it's infiltrated that soil profile. Basically, if you pond water in here, it's the same idea as with the pan evaporation. You pond water in here, and for every 2 minutes you measure how much water has left that pan, refill it, and keep doing that until you reach a steady state infiltration, which we'll look at more in a minute. So the infiltrability or infiltration capacity refers to the rate that water moves into the soil if it's freely available at the soil surface. So again, I said we pond it, so water is freely available there, and that is able to estimate the infiltration capacity. The cumulative infiltration rate refers to the total amount, in this case in depth, of water that is infiltrated over time. So you run this infiltration rate test for an hour, and at 2 minutes your infiltration rate is 10 inches per hour. At 20 minutes it's 3 inches per hour. That's the infiltration capacity. At the end of the hour, the cumulative infiltration may be 60 inches of water. So those are those two different. So soil layers or discontinuities, again I talked about plow pans or shallow restrictive layers. Here's an example of one in this soil profile. They can stop or retard that vertical infiltration of water. You get the relatively uniform infiltration of water in the root zone. It hits this sort of layer and it tends to perch or pond, and then it can start to move laterally. You can see, you might be hard to see, but it's starting to move down this layer over here. So what are some basic soil properties related to infiltration? There's two important ones. Well, there's many important ones. I'm going to talk about two because we'll need them in a few minutes when we look at calculating a water balance. So the basic soil properties I'm defining here are the porosity. And so basically the porosity is calculated as the volume of voids in the soil divided by the total volume of the soil. So it's the total amount of pore space that's in any given soil. So clays tend to have a higher porosity, sands have a lower porosity. And it's constant for a given soil. So a given sand will have a porosity of 25% or whatever it is, and a clay will have a porosity of 45% or whatever it is. Now the soil moisture content varies over time. Again, we looked at soil moisture's effect during the growing season. It tends to fall, goes back up in the non-growing season. So it can change over the course of the day, definitely changes over the course of the growing season. And it's calculated as the volume of water in a soil divided by that volume of that soil. So you have a 1 cubic foot volume of soil, the volume of water, and then there's an estimate of the soil moisture content. So soil matrix properties are also another control on infiltration. So I'm just showing a cross-cut of a soil column here, looking at the matrix properties. So the gray is the solid soil particles. The dark blue is adsorbed water. So this is water that's held on basically by suction to that soil particle. And plants can access this water. However, gravity cannot remove this one. So plants can access absorbed water, but gravity cannot remove it. And then you have capillary water, which is the light blue, and that's water that's found in between, so in those pore spaces in the soil. It's not absorbed into the soil. Gravity can remove this water, and plants can remove this water as well. And then you have the air-filled void spaces. So adsorbed water, capillary water, and air-filled void spaces all combine to create your porosity, your soil porosity. So the infiltration behavior of your soil depends on many factors, but probably the biggest factor is on soil type, right? So here we're showing cumulative infiltration capacity of a soil over time, so 0 to 180 minutes for 6 different soils. So you have a gravelly, sandy loam here and a clay down here. What you can see, and this is relatively intuitive, I think, these gravelly, sandy loam soils have a very high infiltration capacity. They can infiltrate a lot of moisture very rapidly. So, you know, in 60 minutes here, it's infiltrated 400 millimeters of precipitation. So almost half a meter of precipitation in an hour. Whereas the clay, after 200 minutes, it is only infiltrating 20 or so millimeters of soil moisture. So, irrespective of other factors, the clay is going to tend to generate more runoff than a gravelly, sandy loam, provided there's no restrictive layers or things like that in the soil. But soil health and management can also affect infiltration rates. So these are things that we can do as land managers to affect infiltration capacity. So stable soil aggregation can increase the infiltration rate of fine textured loams and clays. So if you can promote aggregation, soil aggregation, you can increase that infiltration rate. Tillage under wet conditions can break down those soil aggregates, so you want to avoid tillage under wet conditions. And then heavy traffic can cause soil compaction, which reduces your infiltration capacity as well. So these shrink swell clays, which we really don't have too much of in this area of the Mid-Atlantic, we do have some in other areas, they temporarily have much higher infiltration rates when they're dry and when they're wet. So when they're dry, they split open and can infiltrate huge quantities of moisture. When they wet up, those soil fractures close and they really behave much more like a traditional clay. So I wanted to just sort of throw up here some of the different factors that influence infiltration. So these are all the factors that influence, I said, not only infiltration, but generally water movement through soil. So you have flow influences, and I think flow chemistry and soil chemistry are important here. So if you have sodic soils, they can reduce the retard water movement. Surface soil conditions, so surface sealing and vegetation cover are both important factors. Hydrophobicity, so some chemicals can reduce infiltration rate by causing hydrophobicity. Subsurface soil conditions, so of course the soil, all these soil components are important. Hydrologic group, texture, porosity, depth, structure, all influence these subsurface conditions. Root systems play a big role, and we'll see some images of that in a minute. Subsurface drainage, this is becoming a greater and greater concern in a lot of our region. And then hydraulic conductivity, so how fast does water move through that general soil. Other influencing factors would include things like frost, organic matter, compaction, and then chemical, biological, and particularly microbial activity. Biological and microbial activity in no-till systems or systems with high organic matter content is important as well. So the infiltration rate varies in time during a wetting event. So what I'm showing here is how the infiltration rate changes over time during, let's say, one precipitation event. So usually the infiltration rate decreases as the soil saturates. And if the wetting continues long enough, we reach what's called steady state condition, and the infiltration rate approaches that constant value. It's not changing very much anymore down here. And so what we see here is that this is for the same soil. Let's say this is a loam, sandy loam soil under two conditions: wetter antecedent conditions. Maybe we got a rainfall event 3 days ago, so it's relatively wet, and then drier antecedent conditions. We haven't had rain for 3 weeks, so it's relatively dry. And what you see here is that under the drier conditions, we can initially infiltrate much more moisture. There's more room in that soil to store moisture, as opposed to the wet soil. But as time progresses, both of these are going to approach the same value, this constant value down here, which is what's referred to as the saturated hydraulic conductivity, and is an important parameter in a lot of engineering design and things like that. So these curves could also represent a no-till. So no-till systems tend to have higher infiltration capacities than tilled systems or conventional till systems, or a uniform soil, or versus a soil with a surface crusting. So those are some sort of management considerations that would affect infiltration capacity. So finally, the cumulative infiltration or infiltration capacity can be limited by the rain intensity and/or the total amount and the soil's ability to store and conduct the water. So looking at this curve, this is the cumulative infiltration or infiltration capacity. So if you have a soil that can't store that much moisture, this curve might look much more like that. Or if you have a soil that can store a lot of moisture, it might go way up here like that. Soils that are already wet or which have a shallow restricting layer, that plow pan or fragile pan, close to bedrock, will have that limited infiltration capacity, even if they have relatively high steady state infiltration. So again, if we think we have a sandy soil overlaying a plow pan, it can infiltrate that moisture very quickly, but it's only going to infiltrate a limited amount of it. So if the soil is a foot deep with 50% porosity, let's say, it can only infiltrate 6 inches of moisture. If that soil is 3 feet deep with the same porosity, it can infiltrate 18 inches of moisture. That's the cumulative infiltration capacity. So I threw in a little quiz here. So which conditions fit the given infiltration curve? So in this one, which curve is for gravel and which curve is for loam? So green and orange. So can anyone tell me which curve is for gravel? Green. All right. How about for this one? So which curve is for hay and which curve is for bare ground? So which curve, green, is which one? Hay, right. So not only can the soil type and soil characteristics affect it, but the management and crop type can affect the infiltration capacity as well. And so I have a little video here. So we're going to talk about macropores a little bit. So macropores are basically large continuous voids in the soil, and they include structural, such as shrink, swell, and tillage fractures, old root channels, and soil fauna. So what you see in this video, we've put a funnel right into a macropore, and we're infiltrating water from this tube into that macropore. I'll play it again because I'll point out how quickly the water is infiltrating into this single pore. So one of these pores might look like this right here. That's a macropore from an earthworm. Look how quickly that moisture, I won't play it again. We were measuring infiltration rates into that single macropore, something like 72 inches per hour. So you could infiltrate a huge volume of moisture into a single macropore in these soils. And this is in a relatively clayey soil. You can see it's pretty clayey down here. Just due to that macropore from an earthworm. This is about 3 millimeters wide. And this is just sort of a diagram of what that might look like. So macropore flow initiation, you get water supply into this macropore, either if it's connected to the soil surface, it can infiltrate directly from the soil surface, or there might be a pool of moisture that can access in the subsurface. And then, water can flow through this macropore and transfer between that macropore and the soil matrix, or continue flowing much deeper into the soil profile. This has recently become a big concern in tile drains, no-till tile drain systems. So you get macropore formation over a tile drain. It's not disturbed by tillage. You can get a lot of flow from that soil surface deep into the soil profile, connected directly to tiles. And I'll show an image of that here. This is another video. So what they did is they attached a pump to a tile and put smoke in the pump. And what hopefully you're seeing is smoke coming out of these macropore burrows directly over that tile. And that indicates a direct connection between that tile and the soil surface. So you can imagine anything applied right to the soil surface is now available to that tile. And so the flow through macropores is favored by several conditions. So wet soil, intense and large amounts of precipitation, and lack of soil disturbance, such as no-tiller pasture. Again, when you till the soil, it destroys those macropores. So there's a trade-off between tillage and conventional till and no-till. No-till reduces surface runoff, but it might increase subsurface losses of certain chemicals. Conventional tillage is going to destroy those macropores, reduce those subsurface losses, but you generally get greater surface losses. So in uniform soils, leaching often occurs in that matrix. So we saw that picture of that dye test where we got relatively uniform flow in the root zone. But then once it hit the zone where we get macropores, we get preferential flow. And so what that is that causes bypass flow of nutrients and chemicals, even those such as phosphorus, which might be strongly absorbed to the soil surface or to the soil, flowing deep into the soil. So this is a picture of a field where manure was just applied. We got a rainfall, unfortunately, right after the manure was applied, and we measured super high concentrations of dissolved phosphate in tile drainage flow in a matter of minutes after that rainfall. And so it was directly connected to that tile system. So sort of trying to tie this all together, I'm going to talk a little bit about soil-water relationships and the soil-water budget, which I think sort of brings everything back together a bit. So the soil-water content. Water content can be expressed in two ways, as a volumetric or as a gravimetric moisture content. So the volumetric water content of the soil is the volume of water per unit volume of soil. And generally it's the most useful way of expressing water if you're thinking about a water budget for a given field or watershed or something like that. Gravimetric water content is the mass of water per unit mass of dry soil. And this would be easier to use when you're making direct water content measurements. So if you wanted to go out in the field and estimate your water content, that's probably the one you would end up using. And they're related. So the volumetric water content equals the gravimetric moisture content times the soil's bulk density. So what does this look like? So this is a soil-water characteristic. So this is the relationship between the soil moisture content or soil water content and the matrix or suction potential of the soil. So we all know that clays right here, this gray line, hold moisture much more tightly in that system. So plants cannot access as much of that moisture or relative content of that moisture as they can from the sand, which is relatively easy to access moisture. And so this is just showing the soil water content by volume percent. So sands at saturation have something like a 35% moisture content, whereas clays are up around 50% at saturation. Down at wilting point, clays will tend to have moisture content somewhere between 10 and 20%, whereas sands it's much lower, it's down around 5% at wilting point. So again, it's much easier to get moisture. It's held less tightly in these sands than it is in these clays or peats or things like that. And again, this shows the relative distribution of those pore sizes. Under low suction, the big pores tend to dominate that soil moisture characteristic curve. Under high suction, the small pores do. The water's held more tightly in the small pores. This is another way to look at it. So this is by soil texture. So sand all the way up to a clay here, loam somewhere in the middle. And what it's showing here is the water content, percent by volume, so the volumetric water content for these different soil types. So this is the wilting point, this line here. Plants cannot access moisture below the wilting point. What you see here is that sands have a relatively low wilting point. Plants can access moisture down to 4 or 5, 6% moisture content in the sand, whereas in a clay, due to the abundance of those small pores where water is held very tightly, they can't access moisture below much like 20%. This line is showing field capacity here, and the difference between field capacity and wilting point is what's called plant available water. So this is water that plants can access in that soil profile. And again, the reason why loams are so highly prized in agri-production, they have the highest available plant available water. A lot of people think clays might, but they really don't because they have such a high wilting point in that clay. And then there's gravitational water. So this is water that can be freely drained by gravity. Soil drainage classifications are another consideration. So what we're showing here is the different drainage classifications: well-drained soils, all the way to very poorly drained or hydric soils, and then the depth that roots can penetrate these soils. So you have a hydric soil. That's anything with some sort of a root barrier at anywhere from 18 inches all the way down to 6 inches. Roots cannot penetrate that barrier, tend to get retarded, reduced production out of those systems, as opposed to these well-drained or aerobic soils. You can get root penetration as deep as the roots can go, essentially. And these are all calculated relatively easily from the web soil survey and things like that. So finally, the final thing I was going to show was how to calculate a soil water budget. Now, I'm not going to go into this basically in just in time, but basically we can calculate how much moisture is in a given field or watershed if we know precipitation, let's say precipitation, how much is flowed in via groundwater, how much is leaving as runoff, evapotranspiration, or surface runoff. So, we can easily calculate all these things and determine how much moisture is in that field or watershed. And this is what it looks like for the Piedmont region of Virginia. So I'm showing periods of excess moisture, so when that soil is wetting, generally during the non-growing seasons, and then when the soil is drying, which is generally during the growing season. So this is the water amount in inches that is available in that soil profile, again, from March through February. So growing season starts right around here. Plants start accessing that soil moisture, so they drop that soil moisture down. It tends to climb back up once crops have been harvested. That's also the time of year when we tend to get most of that excess moisture or groundwater recharge occurring in these areas. So these are important times of the year to refill aquifers in our region. We don't get much aquifer recharge during the growing season in general. So some take-home messages. So understanding how water and solutes move in these soils is important in managing our agroecosystems for optimal productivity and to protect environmental quality. So the processes that we've discussed here can generally be used to plan nutrient management, site BMPs such as buffers or biofilters, time different farm activities like fertilizer, manure application, irrigation, etc. Finally, just say that sound decisions about the use and protection of our water resources requires understanding of these hydrologic processes and how they control water movement and cycles in our agroecosystems. Maybe I have time for a question or two.
Probably a couple questions. Rick, the lights on. Any questions for Zach? All right, evidently everybody's ready for a first round of lunch, so huge thanks to Zach for his presentation.